nonlinear programming problem. And we know that earlier we have a study about linear programming problem. As you know all, that linear programming problem can be solved using simplex method, or if it is in two variable, then it can be solved by using graphical method. Okay, but this is nonlinear programming problem. So as we see that in linear programming problem, all the constraints and objective functions both are linear. But if we talk about nonlinear programming problem, so in nonlinear programming problem, either the objective function or constant will be nonlinear. Okay, so there may be three cases. The first case is that when only objective function is nonlinear and all the constraints are with equality are linear. Okay, it may happen that both objective function and all the constraints may be nonlinear, and it may be happen that objective function is linear but the constant is nonlinear. Okay, so now there are mainly three types of nonlinear programming problems. First one with no constraint, second one with equality constraints, and that can be solved using the Lagrangian method, and the third one is with inequality constraints. So do you know about equality constant and non-equality yeah, inequality constant? As we can see that if we have a constant like x1 plus x2 equal to 4, then this is equality. But if we have like this is less than equal to 4, yeah, it is greater than equal to 4, then these are the inequality constant and this is the equality constant. Okay, so now we move to general representation of nonlinear programming problem. Okay, so if we have a decision variables like n, x1, x2, xn, and we have to optimize the function. There is the means. Optimize means if we have a profit function, then we want to maximize it, and if we have a cost function, then we want to minimize it. Okay, so if there is a word optimize, that means we have to either minimize or maximize. So here the optimization function is in undecision variable, which is x1, x2, and so on, xn. Okay, so the general problem, nonlinear programming problem can be written as maximize. Yeah, you can write minimize a function of x1, x2, and so on, xn. Okay, subject to these are the constant g1 of x1, x2, and so on, xn less than equal to b1, likewise gm of x1, x2, xn less than equal to bm. Okay, where g1 to gm all are the constants. Okay, so here there are n decision variables and f constants. Okay, so we can also write it like this is the summation of j equal to 1 to c jxj. Okay, this series represent the cost of the decision variable. Okay, so this is now you can see here. This is the notation. Okay, so now move to the first part. Nonlinear programming problem with no constraint. Okay, so when there is only objective function are given to find the maxima or minima of objective function. Okay, so what is the working rule to optimize this function? So here we have this function. So for this function, we find the Hessian bolded Hessian matrix. Okay, that will depend on the decision variables. So here you can see that here are n decision variables. So that's why the matrix will be of n times n. Okay, so just calculate the Hessian matrix and second derivative with respect to the first decision variable. Okay, like this, that do f over del x1 square, then x1, x2, then likewise x1, xn. For second one, do the second derivative with respect to x2, then x1, then x2 two times, and then up to this. Okay, so if all the leading principal minors are positive, okay, how to calculate the leading principal minor? As you can see here, this is n by n matrix. Okay, so first leading principal minor will be of n times n. Okay, the next one will be n minus 1 times n minus 1. Just delete the last row and last column. Then it will convert it into n minus 1 times n minus 1. Okay, the next that will be n minus 2 times n minus 2, likewise up to 1 times 1. Okay, so this is the process to calculate the leading principal minor. Okay, then you have to solve it and check whether it is. If all the principal minor with greater than equal to sign, then that function will be minimized. Okay, and if all the leading principal minors are negative definite, that is with alternative sign. Okay, then that function will be maximum. Okay, so this is the working rule when there is only objective function given. Okay, now we move to the next one. Okay, sure. Let us solve the one question related to this kind. So we have find the relative maximum minima of a function. So we have this function, and you can see that this is not a linear function. Okay, because why it is not linear? Because the power of x1 is 2, x2 is 2 also, and x3 is 2. So that's why this is not linear. It means this function is non-linear. So we have to optimize it. So just calculate the bolded Hessian matrix, and you can see that there are only three decision variables, okay, which is x1, x2, and x3. So we can write it like a function of x1, x2, and x3. So this is like this. So now we calculate the bolded Hessian matrix. So just uh, find the partial derivative of this function two times with respect to x1 for this one, then first x1, x2, yeah, you can take first x1, then you can do uh, for x2, so you got this one, likewise this. So we calculate this matrix. So we obtain that this will come to 0, 0, 0, 2, 0, and 0, 0, 2. Now we calculate the leading principal minor. So when you solve it, then you got it. So the third principal minor is it. And if you want to find second, then delete the. You can see here we have this one 200 020 002. Okay, so this is the third principal minor. But if you want to the second principal minor, then you have to delete the last row and last column. So what you got here? You got here 2000. Okay, now you can solve this one. So what you got 4, and if you delete one row and column also, then you got the first principal minor, which is 2. Okay, so this is the process to find the leading principal minor. So you can see here all the principal minor are with greater than equal to 0. So it means all the principal minors are positive definite. So it means the given function is min. Got it? So this is the process to check or verify that the function is either maximum or min. Okay? Using the process of leading using multi-region matrix. Okay? So now we move to the next type, equality constants. Okay, yeah, we can say method of Lagrangian multiplier. Yeah, we can say method of Lagrangian multiplication. Okay, so now there are different cases. So the case first is that when only one constant in two decision variables. So let us see its working rule. So if we have a objective function like that, so we say that there is only two decision variables, so we can write it function of x1 comma x2. Okay, then there's constant only one constant, so we can write g function of x1 x2 equal to b. And there is non-negative condition, so which is x1 x2 greater than 0. So firstly we define a different function. Okay, always write this constant like in this form equal to 0 condition g of x1 comma x2 minus b, and we gave this is function of x1. Okay, you know this b is constant, so that's why we can write like this. So just define like this, h of x1 x2 equal to d of x1 x2 minus b. Now we define the Lagrangian function. Okay, so we need to define a Lagrangian multiplier. So you can see here how to define the Lagrangian function. Just write the objective function. Okay, that is this one, f of x1 comma x2 minus. This is Lagrangian multiplier. Okay, so lambda times this function h of x1 comma x2. So this function is known as Lagrangian function, and lambda is called Lagrangian multiplier. Okay. So now we move to next. So now we find, now we check whether it is maximum or minimum. So you can see here. So let's L, Z, and H may be partially differentiable. So now we apply the condition for maxima and minima. So just partially differentiate Lagrangian function with respect to the decision variable and Lagrangian multiplier. So you can see here there are two decision variable and one Lagrangian multiplier. So we just partially differentiate it. So del L over del x1 equal to 0. Okay. Del L over del x2 equal to 0 and del L over del lambda equal to 0. Okay. So these are the necessary conditions. Okay. Now to find x1, x2 and lambda values by solving above equation simultaneously, we get the point this one. Okay, so now to decide whether z is maximum or minimum at this point, so we find the determinant like this. Just 0 del h over del x1 del h over del x2 like this. Okay, this is symmetrical. So del 2 L over del x1 square, del 2 L over x1 x2. Okay, this is also known as folded Hessian matrix. So now if this determinant less than 0 implies x naught is minimum. Okay, then we find the z minima at x naught And if it is greater than 0, then x naught is maxima, and we find that maxima at x naught. Okay, so now we move to one question related to this. Using the method of Lagrangian multiplier, solve the following nonlinear programming problem. So first one is optimize z equals 6 times x1 square plus 5 times x2 square. Subject to x1 plus 5x equal to 7, and these are the non-negative conditions. So you can see this is your first case as we considered previously, that it have objective function which is nonlinear and there is only one constant. Okay. So now the first way to write this NLPP in the form of this. Okay. So we can write this constant in the form of h. So that can be written as x1 plus 5 x2 minus 7. Okay. So now we write the Lagrangian function that can be written as function which is given here. Here you can say this is z. Okay. You can write it also f. It is your choice. Okay. So minus lambda, this is the Lagrangian multiplier into h. Okay. So this, now you can see here this is 6 times x1 square plus 5 x2 square minus lambda times this is h. Okay. So now to find the condition for maxima and minima, and we calculate the partial derivative of L with respect to x1. You can see here, if you partially differentiate with respect to x1, then you get 12 x1 minus lambda. Okay. So if you calculate partial derivative with respect to x2, then you got tan x2 minus 5 lambda equal to 0. And if you partially differentiate with respect to lambda, then you got this one. So from these equation, we need to calculate the value of h1, x2 and lambda. Okay. So you can see here from the first one, we can calculate the value of h1 in terms of lambda. Also from this one, we calculate the value of x2 in terms of lambda. So now to calculate this value, we just put the value of x1 and x2 in this equation. Okay, so after solving these, we got x1 equal to 7 over 31, x2 equal to this one, and lambda equal to this. So the point x naught is 7 by 31 and 42 by 31. So now we calculate the value this determinate. Okay, so when we solve it, then we check that this is less than 0. So since this is less than 0, so x naught is minimum. Okay, so z minimum will be this one. Then put the value of x naught, x1 and x2 here, then we got this one. So any doubt? Now the case 2, and decision variables with one equality constants. Optimize z equals function of x1, x2 and so next. Okay.